Namaste and welcome to this lecture on linear algebra through geometry. In the last few lectures we focused on 2 dimensions, vectors in 2 dimensions. We looked at transformations of vectors. We also tried to relate to the idea of system of equations. How does this system of equations in solution to the system of equations, how does that kind of get connected to the idea of vectors, and we looked at the equations in terms of the matrix transformation. We looked at the equations system of equations as Ax equal to b, and then when we were trying to solve let us say for x, equivalently we said that in the vector perspective x corresponds to the scalars that we need to find out, so that you can write the right hand side vector b as a linear combination of the columns of A. And in that process we also looked at the idea of determinant of a 2 by 2 matrix, which we said that it is actually the area of the parallelogram formed by the 2 column vectors of the matrix A, which is a 2 by 2 matrix. And from there we looked at the idea of consistency, then homogeneous system of equations and all those things. And we also looked at various linear transformations of 2 dimensional vectors in terms of rotations, reflections, scaling, shearing and all those things. Projections also we did. Towards the end of the module 3, we also module 4 we also looked at the idea of eigenvalues and eigenvectors. That means these are the vectors which do not change the directions when a transformation A is acting upon the vector. That is exactly what we saw, and we also found out ways to obtain the eigenvalues and the eigenvectors. We did all that in the previous lectures. Now from this lecture onwards, for the next couple of modules we will be talking about vectors in 3 dimension. That means we are going from vector with 2 components to vectors with 3 components. In 2D we had x1, if you have a vector x, we said that the vector had 2 components, namely x1, x2. In this case what we are going to do is we are going to look at a 3 dimensional vector. So in a sense we are going to add one more component to it. So any vector x is going to be expressed as a 3 component vector x1, x2, x3, and then we are going to look at a few interesting things as far as the 3 dimension space is concerned. There are a few things which do not happen in 2 dimension and but happens in 3 dimensions. So those things we will be focusing on. We will follow the same approach as the previous modules, where we will look at ideas of vectors in 3D and transformations and stuff, and then we will go ahead with solving system of equations in terms of the Gauss elimination, which you would have done in module 2, Gauss elimination technique and stuff. And then we will again try to relate to the system of equations to the idea of 3 dimensional spaces, then vectors in 3D. We will figure out how do we connect these things, and then later we will get into the idea of a general vector spaces in future modules. So let us get on to 3D space, explore 3D space. Okay. So any vector in 3D we are going to write, and in all these cases we are just going to focus on vectors which have the components which are real numbers. So we are going to say that a vector in 3D. So we will just take, this is 3D. So we are going to take a vector, let us say a vector x in 3D. X in 3D is expressed as, is defined or denoted or expressed as, defined as a triple of numbers. So basically we are going to say as x is equal to x1, x2 and x3, right. So and we are also going to say that say a set of all vectors in 3D space, in 3D space we are going to call this as R3 like how we said, like set of all vectors in 2D space, we are going to call that as R2. Now what does this actually mean? It is basically Cartesian product of 3 real numbers, basically x1, x2, x3. So you are going to call that as R3, and this you are going to call it as R2. Now like how we started in the first case, so any vector, now x is going to be expressed as a triple of numbers x1, x2, x3, and therefore it is natural that how do two vectors combine, how do the vectors get scaled in 3D, all those things. So we will look at those basic operations right now in terms of vector addition and scalar multiplication of vectors and see what happens. Okay. So let us look at this. So suppose we have two vectors. Suppose u is a vector which is u1, u2, u3, and v is another vector which is v1, v2, v3. We define the vector addition in a manner which is similar to that of 2 dimensional vectors. We do a component wise addition. So I am going to define this vector w as the vector u plus the vector v, which is component wise addition. So I am going to take this as u1, u2, u3 plus v1, v2, v3, and the vector w is going to be given by u1 plus v1, u2 plus v2, and u3 plus v3. Yeah. So the components of the vector w, which is basically say w1, w2, w3, is going to be the component wise sum of the two vectors u and v. Similarly, we can look at scaling of so this is basically vector addition. So let us write this vector addition. W vector is equal to u plus the vector v. Similarly, we are going to look at scaling of vectors. So say scalar multiplication of vectors. Scalar multiplication. Say suppose we take suppose C is a scalar, C is a scalar, that means C is a real number. Let us assume that C is a real scalar. Then the vector, let us say w, which is, or let us say the vector, let us look at this. So let us take this, let us take the vector z is basically given by C times u vector, which is nothing but C into u1, u2, u3. This is the same way that we do scaling as in the case of 2 dimensions. So this is going to be C u1, C u2, C u3. That means every component gets multiplied by the same value C. That is how we define our scalar multiplication of a vector, right. Now recall that in 2 dimension, in 2D, we could actually do this. We could express, we expressed any vector, we expressed any vector, let us say u is equal to u1, u2 as u1 into 1 0 plus u2 into 0 1, and we say that this is basically u1 into the e1 vector plus u2 into the e2 vector. So basically saying that if I have a vector which is, this is say u and whose coordinates are u1, u2, it simply means that I walk a distance of u1 along the vector 1 0 direction. This is basically the point u1, and along the y direction, along the u2 direction or along the 1 0 direction, I walk a distance which is u2. So essentially this vector is u1 times 1 0 and this vector is u2 times 0 1. So, this vector u is equal to u1 u2, you can express it as a linear combination of the vectors e1 and e2. So, along the similar lines, a vector in 3D any vector u can be expressed as u is equal to u1 u2 u3. We can express this as u1 into 1 0 0 plus u2 into 0 1 0 plus u3 into 0 0 1. So, basically here again we have the idea of u1 e1 plus u2 e2 plus u3 e3, where the e1 vector in this case is going to be the 3 component vector 1 0 0, e2 vector is going to be the vector 0 1 0, and e3 is the third vector which is 0 0 1. Yeah. Now, it is interesting to note that in case of 2D, we had this. I am just doing the I mean ensuring that the understanding is clear. So, I am just doing 2D and 3D side by side. So, in 2D we had this, where suppose I had a vector u which was let us say u1 u2 and the vector v which was v1 v2. We said that the vector w, which is basically the sum of these two vectors u plus v, which is equal to u1 plus v1 and u2 plus v2. This vector corresponded, this vector was basically the diagonal, it was in the direction of the diagonal of the parallelogram, formed by u and v, parallelogram formed by u comma v, the vectors u v. What does that mean? That simply meant that if we have a vector, this is say u, and let us take this vector which is v, and all we need to do is we need to complete the parallelogram. So, I have this is again the u vector, and that is going to be the v vector, and the diagonal that we have, this is basically the vector u plus v, right, that is a vector u plus v. Now, how does that happen in 3D? In 3D it is a bit tricky, because here what we did is we basically walked along the direction of I mean we did this, we walked u1 units along the x axis and then u2 units along the y axis. Similarly, we had walked along v1 units in the x axis and v2 units in the y axis, and then we tried to add these things. So, now what we do is we are going to look at the same thing, probably what would I say, in case of our 3D. Suppose I am going to just take this vector u, which is going to be say u1 u2 u3. I can express this as u1 into 1 0 0 plus u2 into 0 1 0 plus u3 into 0 0 1. How does this look like? Basically, let's just get a, let's look at it in a graphical way with all kind of visualization. So, let us assume that this is going to be the E1 axis, this is going to be the E2 axis, and let us say this is going to be the E3 axis. So, assume that these are orthogonal axes that we have. So, I have E1 along this side, I have let us say E2 along this side, and I have E3. This is the direction of E3 corresponding to my x, y, z and x, y and z axis, or x1, x2, x3 axis. So, what is it going to be? So, what does it say? Along the direction of 1 0 0, I walk a distance which is let us say u1. This is going to be u1 0 0. And let me mark all these things u1 0 0, u2 0 0 and u3 0 0. So, this is going to be, let us say this is going to be 0 0 u3, that is the direction of this vector 0 0 u 3, and let us take one more which is basically along this direction, which is basically let us say along this direction. Let us call this vector as 0 u 2 0, right, 0 u 2 0. Now, how does all these things look like? That is what we need to see, right. Okay. So, now what have I done? I have u 1 0 0 and this is the vector which is 0 u 2 0. So, what I do is I know how to complete the parallelogram here. So, what I do is I draw this parallelly. So, I basically get to the vector which is u 1 u 2 0, yeah. I get u 1 u 2 0, and from similarly what I get here is I complete the parallelogram here also. Let us look at this. So, I have this guy, I have this. Similarly, let me do this also here. So, I have this, and this is going to be parallel to this vector, and I am going to have one more here which is basically the green vector which corresponds to my 0 0 u 3. So, I am going to have one more parallel here which is this. Let me complete this prism that I have. So, what does this look like? I have gone from u 1 0 0 and I have added this vector which is basically 0 0 u 2, I mean 0 u 2 0, and at that when I get that resultant to that vector, what I am doing, I am adding this vector 0 0 u 3. So, this is going to be the vector u 1 u 2 u 3, that is the resultant vector. So, if you look at the resultant vector, it is going to be something like this. It is going to be from here to the, it is like a diagonal segment of your rectangular prism. So, the resultant vector that you get here, which is basically our u 1 u 2 u 3, this vector is going to be the diagonal segment of a rectangular prism, of a rectangular prism. And what is the condition? We see that the edges of the prism, are parallel to the reference axis, are parallel to the reference axis or the coordinate axis. Coordinate axis, yeah, okay. So, we can actually the moment we understand this, it is easy to define the linear combination of vectors in 3D, like how we did linear combination of vectors in 2D. We can define linear combinations of vectors in 3D, linear combinations of vectors in 3D. How do we do that? We already know what it is. Suppose we say the vector w, if it can be expressed as, let us say alpha 1 u plus alpha 2 v, where alpha 1 and alpha 2 are scalars and the vector u is basically this vector which is u 1 u 2 u 3, and the vector v is basically v 1 v 2 v 3, right. So, what we say is w is a linear combination, it is a linear combination of vectors u and v for some real scalars, for some real scalars alpha. The moment we define the linear combination, we actually got into the idea of linearly independent and linearly dependent vectors. So, we say that if u and v are vectors are in R3, that means there are 3 component vectors as before. We are, if u and v are in R3, then u and v, the vectors u and v are linearly dependent. We already know this definition of linearly independent and linearly dependent from the idea of 2 dimension. We are going to say they are linearly dependent if u can be written as k times v, that for some scalar k, for some scalar k, right. Okay. Now, but we have already seen that any vector u is actually expressed as a linear combination of 3 vectors, namely the E1 vector, E2 vector and E3 vector. Therefore, natural question is to ask what happens when we have 3 component vectors u, v and w. If we have 3 component vectors, how do we define the idea of linearly independent and linearly dependent in that case? So, what we are going to do is we are going to say that if u, v, w are and w are vectors in R3, then they are linearly dependent if one of them can be expressed, one of them is a linear combination of the other two, linear combination of the other two. Of course, we know 2 of those vectors, if they are linearly dependent, you are going to say that one is the scalar multiple of the other. If they are going to be, if you are going to have 3 vectors, then they are linearly dependent if one of them can be expressed as a linear combination of the other 2. A linear combination of the other 2 could simply mean, okay, suppose I can have this also. For example, I can have this u is equal to, let us say 1, 2, 3 and v is equal to, let us say 2, 4, 6 and w is equal to, let us say 3, 6, 9. Now, we see that v is equal to 2 times u and w is equal to 3 times u, and therefore, we say we already figure out that these 3 are linearly dependent vectors. Let us take another simple example. For example, this is example 1. Let us take example 2. Suppose I have this vector u is equal to, let us say 2, 1, 3, v is equal to 1, 4, 2 and let us say w is equal to 5, 13, 9, then we see that u plus 3v is going to give me w. That means, what does that imply? We have 2, 1, 3 which is u plus 3, 12, 6, that is going to give me 5, 13, 9. Therefore, we say that the vectors u, v and w are linearly dependent. However, it is interesting to see, however, we see that we will say that we see that the vectors E1 which is equal to 1, 0, 0, E2 which is equal to 0, 1, 0 and E3 is 0, 0, 1 are linearly independent vectors. we can very clearly see that none of them can be expressed as a multiple of the other or linear combinations of the other two guys. So, linearly independent vectors. In fact, if you look at the structure of E1, E2, E3, you can very clearly see that they have one in distinct positions, and therefore, and the other two components being 0, one cannot be written as the multiple of the one vector cannot be written as the multiple of the other, and one of the vectors cannot be even written as a linear combination of other two vectors, in which case we say that these three vectors E1, E2, E3 are linearly independent. Is that clear? So, that means none of these two can be expressed as a linear combination of the other two guys. Okay. So, that brings us to the idea of that clearly tells us what we mean by linearly independent vectors in case of 3 dimension. When you have only 2 vectors, it is easy to see whether one of the vectors is a multiple of the other. However, when you have 3 vectors, let us say 3 component vectors, which are you have 3 component vectors or 3 vectors from R3, all you need to do is check whether if one of them can be expressed as the linear combination of the other two, or if one of them is a multiple of the other. That says that the set of 3 vectors is going to be linearly independent or dependent. Okay. Now, the next thing that we did is the moment we looked at the vector, the idea of vector, we looked at the magnitude or the length of the vector, the magnitude of the vector or the length of the vector, which is basically given, which was given by Pythagoras theorem in case of vectors in 2D. So, let us look at so for a vector in 2D, for a vector u in 2D, u1, u2, u1, u2, the length of this vector u was given by Pythagoras theorem, which is square root of u1 squared plus u2 square. This is what we had. Analogously, we can actually say that analogously for a vector in 3D, for a vector v, which is v1, v2, v3, we have the length of this vector v is given by the same idea that we have, which is nothing but square root of v1 squared plus v2 squared plus v3 squared, right. So, and we defined this square root of v transpose v, square root of v dot v, and we also know that if u and v are two vectors, then we defined the dot product of the two vectors, which gave me a scalar, which was given by u dot v is equal to u1 u2 u3 dot v1 v2 v3, which was basically u1 v1 plus u2 v2 plus u3 v3, and we also set this u dot v as the magnitude of u multiplied by the magnitude of v and cos theta. This is what we had. If the same definition holds good, if cos theta is 0, then u and v are orthogonal. We are orthogonal. Yeah, we use the same idea of what would you call, we use the same idea that we studied in 2 dimension. We are going to use the same thing to figure out whether 2 vectors in 3D are orthogonal or not. Therefore, we got this idea of finding cos theta, or the angle between the 2 vectors, as cos theta is equal to the dot product of the 2 vectors divided by the magnitude of the 2 vectors. This is what we had, right. Now, the question is, we figured out that if there are 2 vectors in 3D, we can find out the angle between the vectors, and we also figured out how to find the length of the vectors. We also found out if you have 2 vectors, what is the resultant vector, how do we geometrically interpret the resultant vector. We also looked at the idea of linearly independent vectors or linearly dependent vectors, where in which we said that in 3D, if you have 3 vectors, if one of them can be written as a linear combination of the other, then the 3 vectors are said to be linearly dependent. If not, you call that as linearly independent. So, we looked at all that. Going forward, where are we, what are we trying to do with the idea of dot product, what is it that we can find out. So, we will go ahead in the next module, we will be seeing that I mean how are we going to apply this idea of cos theta, where in which we are going to look at projection of a vector onto another vector. We are going to look at projection of a vector onto a plane passing through the origin, we are going to look at projection of a vector onto a line passing through the origin, and then we come to a very important concept of 3 dimension, which is basically the cross product of 2 vectors. So, we come to the idea of cross product of 2 vectors, and once we do the idea of cross product, we also look at the idea of area of a parallelogram here, like what is it to say that if there are 2 vectors in 3D, what is the area of the parallelogram that is formed by these 2 vectors in 3 dimension, and because it is in 3 dimension you have one more component added. So, what is it that we have already seen, that you have a rectangular prism, like that is what we had seen when we wrote a vector u as u1 e1 plus u2 e2 plus u3 e3 for scalars u1 u2 u3. So, we want to find out what is the volume of this rectangular prism, and those things will form the topics for the next module. Thank you.